Hello class, hello students. Uh, we will be starting with the new topic today concerning the development of FEM equations for a beam element, and we will be using the same approach which has been used in the previous terms for developing the equations of a bar element. The equations of the bar element were developed using the direct stiffness approach. The equations in fact were developed using the elementary strength of materials theory developed in your BTech classes. And then, depending upon the sign conventions, uh, we simply uh, converted the relationships obtained between force and displacements to FEM equations. I'm just repeating the process once again. We use the basic SOM theory developed in the BTech classes to obtain the relationship between force and displacement. And then the next step was the sign convention. Uh, we compared the directions of forces and displacement as we use in SOM theory to what is going to be used in FEM theory, and simply on the basis of this particular sign conventions, the stiffness matrix was obtained for the case of a bar element. In this case also, in the present lecture also, we are going to do the same thing. Uh, Beam obviously is one thing which you have already studied in your BTech classes, and beam is going to be subjected to transverse loading and movements, which is going to deform the beam. So deformation of the beam is going to be tackled with respect to the vertical deformation also, and with respect to the angular deformation also. So when you compare a beam element with a bar element, a bar element has only 1 degree of freedom per node, that is the axial deformation. But when we talk about beams, a beam is going to have 2 degrees of freedom for each node. One of them is going to be the vertical deformation, and the other is going to be the angular rotation. So this is the first difference between the bar element and a beam element. And the second thing is a bar element supports only axial forces, but the beam is capable of taking vertical loads or transverse loads as well as movements. So there are two types of disturbances which are acting on the beam, and there are two types of responses, and that is the vertical displacement and the angular displacement, which is found in beams. So this means uh, that the relationship which is supposed to be obtained over here from the basic beam theory is a relationship between forces and moments to vertical displacements and angular rotations. Obviously, this particular relationship are going to be obtained using basic beam theory. So we start with the lecture for today with a brief introduction to beams. A beam is a long, slender structural member generally subjected to transverse loading that produces significant bending effects as opposed to twisting or axial effects. The thing is that the beam is capable of sustaining transverse loading, but the majority of effects which are going to be produced are going to be the bending effect compared to the twisting or the axial effects. This bending deformation is measured as a transverse displacement and a rotation. Therefore, the degrees of freedom considered per node are going to be transverse displacement and rotation as opposed to only a axial displacement for a bar element. So this happens to be a first difference between the beam element and a bar element. Now using the Conventional theory of strength of materials. This is how a beam element is going to be taken up when we draw the equilibrium diagrams. We have the shear forces acting at the two ends indicated by V, and correspondingly there are two moments at the two ends. Please note that the direction of forces and the movements which have been drawn in this particular figure. In the left hand side, the vertical force is acting upwards, and in the right hand side, the vertical force is acting downwards. These are the positive directions. But when you consider movement at the left hand, the movement happens to be clockwise, while in the right hand, the movement happens to be in the anti-clockwise direction. But when we deal with the FEM element, FEM beam element, uh, that is going to comprise of two nodes, node 1 and node 2, the direction of both forces and is going to be positive in the positive y axis. The direction of both forces is going to be positive in the along the positive y direction. And similarly, the moments are going to be taken as positive when they are acting in the anti-clockwise direction, and also the displacements, angular displacements, are going to be positive when they are in the anti-clockwise direction. This obviously can be compared to what is shown for the strength of materials element. You can very well notice that at the left end, uh, moment m1 is considered to be positive when it is acting in the anti-clockwise direction. But from the strength of material theory, the moment m is positive when it is acting in the clockwise direction. Similar comparisons can be made for movements acting at node 2 and forces acting at node 1 and node 2. Now, strength of materials also give us a number of relationships between deformations and movements and shear forces. The relationship which we are going to use in the present discussion are going to be equation number 1, which relates the bending moment to the transverse loading, that is transverse displacement. This happens to be a second order relationship. Then the relationship between shear forces and transverse displacement. In this, obviously, there is a third displacement, third differential present. Then equation number 3 gives us the required governing equation, in which the notations which we have followed is m represents the moment, v happens to be the shear force, e represents elasticity, I happens to be the area moment of inertia, w small w is distributed loading, and v represents the vertical displacements. So depending upon these four equations, we are going to obtain the relationship between uh, moment and shear forces against the transverse displacement and rotation. And since the beam has 4 degrees of freedom, the beam element which we are taking happens to be a two-noded element. But since both the nodes have 2 degrees of freedom, that gives us a total number of 4 degrees of freedom for the beam element. Therefore, the polynomial which we are going to choose is going to be a cubic polynomial because it has 4 unknowns, a1, a2, a3 and a4. The order of the polynomial which has to be chosen is always going to be is always going to depend upon the number of degrees of freedom of the element. And since in this particular case the number of degree of freedom happens to be 4, we are choosing a cubic polynomial. Now this particular relationship obviously is going to be used to represent the deformation in the beam element. Notice that the number of A's, that is the number of unknown, happen to be same as the number of degrees of freedom. In the next step, the we are going to relate A's in terms of degrees of freedom. So we have carried forward equation number 0. This was the same equation which was illustrated in the previous slide, and since it has been carried forward, it is kept in the top, and this is equation number 0. So at x is equal to 0, that is the left end, the transfer displacement is going to be, that is x is equal to 0 is going to be substituted in equation 0 to get equation number 1. Similarly, we are going to differentiate equation 0 and are going to substitute x is equal to 0 in the resulting equation to give equation number 2, which obviously relates the angular deformation at node 1 to A3. Now, similar expressions can be obtained for x is equal to L, that is the right end, to get equation number 3 and equation number 4. Now, these four equations can be solved to get the value of the four unknowns, that is A1, A2, A3 and A4. And after solving, what we get is equation number 0 when the value of A1, A2, A3 and A4 is solved, and these four expressions are substituted in the uh, cubic polynomial. What we get is expression number 0, which can obviously be written in a matrix form and written in equation number 1, which relates the transverse displacement to the 4 degrees of freedom. In this particular equation, n represents the corresponding shape functions, and the degrees of freedom are represented by a matrix B matrix, that is equation number 2, and the shape functions, because we have 4 shape functions involved corresponding to 4 degrees of freedom. This is equation number 3, that basically is a row matrix, and these happens to be the expressions for the 4 shape functions, that is in equation number 4, 5, 6 and 7. Now equation number 0, which is a equation for the transverse displacement, is now going to be used to obtain the expressions for shear forces and moments acting at the two ends of the beam. So this gives you equation number 1 for shear force, which has been evaluated at x is equal to 0, that is the left end. Similarly, equation number 2, which is the bending moment, evaluated at x is equal to 0. And similar expressions are going to be obtained for the shear forces and bending moment at x is equal to L, that is the right end. These are the forces and moments as obtained from the Sohm theory. And the last step is to compare the Sohm theory with FEM theory as explained in the next slide. In this particular slide, we are going to compare the directions of shear forces with respect to movements and directions of transfer displacement and angular rotations at the left end and the right end. So what we get is that at node 1, the direction of both the forces and the shear force happens to be along the same positive y-axis. So F1y is equal to V. This is equation number 1. But you also notice that the direction of movements happens to be opposite to each other. So m1 is going to be minus m. This is equation number 2. Similarly, at node 2, the direction of forces happens to be reverse. So we get equation number 3. And the direction of movement happens to be along the same direction. Both of them are anticlockwise. So m2 is equal to 4. This gives you equation number 4. These 4 equations obviously have been obtained using the sign conventions which are followed in the traditional beam theory and in the FEM theory. Now, depending upon these uh, relationships, that is F1, F2, and F3 and F4, what we are going to get is equation 5, equation 6, 7, and 8. Now, these 4 equations obviously relates the expressions of moments and vertical forces and the shear forces for traditional zone theory and the beam theory of FEM. And in the next slide, we simply are going to uh, express these 4 relationships in a matrix form as equation number 1. On the left hand side, we have the 4 forces F1y, M1, F2y, and M2 expressed in a relationship against V1 phi1 and V2 phi2. Obviously, the matrix involved in between happens to be the stiffness matrix, which relates the left hand side to the right hand side. So this is basically the stiffness matrix. What basically should also be observed is that the stiffness matrix, this stiffness matrix is also a symmetrical matrix, as we have obtained in the case of a bar element, which was discussed on the previous term. Now, once the stiffness matrix has been obtained, we can obviously utilize this stiffness matrix to solve some beam problems. So, we are taking an example. The example which we are taking happens to be a cantilever problem, which has a vertical force acting downwards and a moment acting in the anticlockwise direction uh, at the center. Since the vertical force is acting downwards, it is written with a negative sign because the positive y-axis is towards the upper direction, and correspondingly the moment is in the anticlockwise direction. So that happens to be a uh, with a positive sign. This negative and positive has been decided with respect to the FEM theory. So we divide the entire beam into 2 elements, element number 1 and element number 2, and correspondingly they are going to be 3 nodes, node 1, node 2, and node 3, as indicated in the figure. Both the elements have been chosen to be of equal length. This has basically been done to simplify our calculations. We don't want our calculations to turn up to be a complex one, because after all we are dealing with the example itself. The knowns are, since the node 1 is fixed, the transfer displacement as well as the angular rotation at node 1 is going to be 0. We have forces and moments applied at node 2. So obviously these two are the known quantities, and the right end is simply supported. Therefore, the vertical displacement is known, it is going to be 0. but the angular displacement obviously is going to be a unknown quantity. The unknowns are F1 and M1 that are the reactions at node number 1, V2 and phi 2 that is displacements and angular rotation at node number 2, and phi 3, F3 and M3 at node number 3. Now coming to something about degrees of freedom. The degrees of freedom for element number 1 are: node 1 has 2 degrees of freedom indicated by V1 and phi 1. Node 2 also has 2 degrees of freedom indicated by uh, V2 and phi 2. This is for element number 1. Similarly, for element number 2, node 2 has 2 degrees of freedom, V2 and phi 2, and node 3 also has 2 degrees of freedom, V3, phi 3. So each element has 4 degrees of freedom. 2 of them happens to be transverse displacement and 2 happen to be the angular displacement. But when you talk about the beam as a whole, there happen to be 3 nodes. So obviously there are 6 degrees of freedom. 3 of them happens to be vertical displacement and the other 3 happens to be the angular displacements. So starting with the solution now, starting with element number 1, which has node 1 and node 2, and the expression for the stiffness is also written on in this slide. So stiffness K1 is going to be given by this expression, and please note that the degrees of freedom have also been written along with the stiffness. This is what we get for equation element number 1. Similarly, element number 2, we get its stiffness along with the required degrees of freedom. Now, once the degree of freedom, once the stiffness matrix of both the elements have been calculated, the next step comes, the next is the assembly step. And since the entire domain has 6 degrees of freedom, so the stiffness, the global stiffness matrix is going to be a square matrix of size 6 by 6. So we have a square matrix, zeros filled with zeros, and the corresponding degrees of freedom have been written starting from V1 phi 1, V2 phi 2 to V3 phi 3. These degrees of freedom have been written to simplify our process of assembly. Now, starting with the first element, this is what you get when you assemble, when you transfer the stiffness matrix of the first element from the local to the global matrix. The contributions of the first element have been written all in black. Now, coming to the second element, when you start with the second element, the global matrix is already going to contain contributions from the first element. So obviously this means that there are going to be some places where the contributions of element number 1 and element number 2 are going to overlap. And since element number 1 and element number 2 has node 2, which happens to be common to both the elements, so this means that since node 2 has the 2 degrees of freedom of node 2 are V2 and phi 2, the stiffness matrix are going to overlap at places corresponding to V2 and phi 2 in the global stiffness matrix. So this is what you get as the assembled global stiffness matrix. The contributions from the first element are written in black, and the contributions from the second element have been written in red. So columns and rows corresponding to V2, Phi2 obviously can be seen that they have contributions from both the elements. And once we get the global stiffness matrix, then obviously the next step is uh, the substitution of the boundary conditions to get the solution. And at this particular point, it's going to be worth mentioning that the stiffness matrix, the global stiffness matrix is going to be uh, a singular matrix, because we have already discussed previously that all the matrices which we are going to get are going to be singular unless we have some boundary conditions imposed on them. So we have the global stiffness matrix and five known parameters, and the unknown happen to be F1 M1, V2 Phi2, Phi3, F3, M3. So the next step is going to discuss the solution method. This is the global matrix, and since V1 is known, it happens to be 0. The process which the easier process which we do for the manual calculation is that we simply strike off the rows and column corresponding to the known parameter, especially when the known parameter happens to be 0. But when the known parameter have a non-zero value, then this particular process which is going to be illustrated just now is not really going to be applicable. Then we have some other process. But for the case when the known parameters happen to have zero value, we simply strike off the corresponding rows and the columns. So we strike off the first equation and we strike off the first column. The next parameter is phi1 is equal to 0, which happens to be the second, which happens to correspond to second row and second column. Therefore, the second row and the second column also gets struck off. Next is V3 is equal to 0, which corresponds to fifth row and fifth column. So fifth row and fifth column also is going to be struck off. This means that in our solution process, we are not going to use equation number 1, equation 2 and equation number 5, and correspondingly the equations which now are going to be used are equation number 3, 4 and 6, which basically are going to depend upon V2, phi 2 and phi 3. So we have three equations and the unknowns are V2, phi 2 and phi 3. So and we have M2 and F2 which are known. M3 obviously is a free end. Node number 3 corresponds to a free end. It's not a fixed support, it's a simply support which obviously cannot sustain any moments. So the value of M3 is going to be 0. Now what we get now is a set of three simultaneous equations. We have three unknowns which can be solved, and once the value of V3, V2, phi 2 and phi 3 has been calculated, we can get the corresponding value of forces and moments acting on the individual nodes. And as a last step, we can we can draw the shear forces and bending moment diagrams. So this is all about um, the lecture for today. In the next lecture, we are going to deal with the potential energy theory, and something is going to be discussed regarding the distributed loading on the beams, because for the time being what we have simply done is that we have illustrated how what is supposed to be the solution procedure when we are dealing with point forces and point moments. But the thing is that the beam can support distributed loads also. So how the distributed loads are supposed to be tackled, this is going to be the topic for the next class. For the time being, we simply close this particular lecture, and we are now going to discuss your problems now.